Hello. In this video, we are going to cover the normal distribution. So the normal distribution is a type of probability distribution that's used for modeling continuous distributions. It is extremely popular. Just writing that down. It is popular. So you see it very, very regularly. Why is it so popular? It's popular because of the sheer volume of different circumstances under which it can be used. The examples include things like natural phenomenon, like heights for men and women. We're going to look at an example in this video for the length of seal pups. It does a great job modeling like random events, like travel times. Let's look at an example, and I can maybe try and give some light as to why is it so popular. So here's some examples of this is just data collections. So these look kind of like data that we collected earlier in the semester. They're presented using a histogram. We've got cholesterol versus the number of frequency, the number of people who have different levels of cholesterol. Blood pressure, similar. You've got histogram bins here where you have frequency. We have heights for people. So these are all examples of things that. And then my apologies, but so what is the distribution? What's the normal distribution? It's this curve. All right, that is that shape. That shape ends up being extremely popular when it comes to modeling things. Now, what are the characteristics of that shape? Well, so it's unimodal and symmetric. So data is frequently unimodal and symmetric. And then it has a declining pattern as you go out from the center. So what it's saying in a sense is that the most popular results are near the center, and you get less popular results as you move out from the center, as things become more extreme. So with distance from the center, with extremeness in terms of measuring the distance from the center, you get less data. And that models lots of different situations. If you thought about throwing horseshoes, you're probably going to find that your throws, if you go through and measure their distance from something, that your throws are kind of in a relatively small area, and extreme throws, like where you throw it way too far or it's way too short, those are less common. So it's the nature of the structure fits the nature of randomness in a way, and so that's why it's so popular, is because of that connection. All right, let's jump back over here. All right, so what are we going to do with it? Let's first go through and define some stuff. So we're going to let's talk about center and spread. So what we're going to do is we're just going to inherit the ideas that we've already discussed from earlier in the semester. So what were the ideas from earlier videos? What were the ideas that we covered when it comes to unimodal symmetric distributions? Well, they were the idea of mean and standard deviation. So our normal distributions are going to have a mean and a standard deviation. So the mean, we're going to go through and we're going to use a different symbol for the mean. The reason is that although it's maybe a little bit subtle, a normal distribution is not exactly the same thing as what we covered earlier in the semester. The reason is that a normal distribution is a probability distribution. So it inherits all of the things that we covered in the last video. Whereas data, the graphing data that we did earlier in the semester, those data, they were the histograms where you had frequency as the y-axis. Those are not probability distributions. They are data distributions. You're just presenting the distribution of the data. So those are not exactly the same thing. The difference between them is a little subtle, but we're going to go through and we're going to use a different definition, a different symbol for the mean to separate the two. So we're going to use the symbol mu, Greek letter, and then for the mean and for standard deviation, we're going to use sigma. All right, so in terms of what we're going to do with these, so just like earlier in the semester, the mean is going to represent the center, and the standard deviation is going to represent the spread. So the standard deviation basically separates thin and tall normal distributions from wide and short. Okay, so what do we mean by that? Let's look at it. Let's look at a picture so you can kind of get some idea of what we're talking about. All right, so what we have here is we have a couple of normal distributions. So normal distributions have this I can't remember if I said it a minute ago, but it has this what's called a bell shape, and that shape can be taller. I mean, you can have different heights for it. It's not necessarily where the distribution is exactly the same shape. You can go through and use the standard deviation to spread it out. And if you have, in this case, I believe that these two have the difference between the standard deviations is that they're double. So I think the standard deviation for this inner one, I think it is 1. So I think this has sigma of 1 for this guy. And I think this guy has a sigma of 2. I think so. And then so you see what the effect of that is that the sigma of 2, it looks like it's about twice as wide, right? So if you just kind of eyeball it, looks like the bottom here ends around 3 standard deviations, right? These look like these are standard deviation counts. So you have 0, 1, 2, 3. It looks like it ends around 3. And then the wider one ends around 6. So that tells you that the standard deviation for the wider one is double. And then the effect that's kind of interesting here is that if you look at the difference between the heights, is that the height of the thinner one is 0.4, the height of the shorter one is 0.2. And so when you double the width, you half the height. So that's kind of cool. All right, so that's kind of interesting. But both of these have the same general shape. You have that that peak in the very middle, and then it levels off and decreases until it goes down until it goes close to 0. They both do the exact same thing. They just do it over different widths. Okay, so when it comes to going through and defining normal distributions, the only differences between normal distributions are the mean and the standard deviation. nothing else. And so because of that, what we're going to do is we're going to actually create a symbol here. So we're going to use capital N to represent a normal distribution, and then we'll have mu and sigma. All right, and so we'll be able to go through and just write this, this notation, and that will represent that we mean a normal distribution. And the first thing is the mean, and the second is the standard deviation. All right, and hold on, actually, there's one more example I was going to show you. So what we've got here is we have two normal distributions for heights of men and heights of women. So it doesn't look like it went through and defined this, but the heights of women are represented with n of 64, 3, and then men n of 69, 3. So the thing that's interesting, really interesting about this result is that the standard deviation for men and women is the same. These are in inches, by the way. So the mean height of women is 64 inches with a standard deviation of 3 inches. The mean height for men is 69 inches, where the standard deviation is also 3 inches. And so when you go through and graph the two results, because the standard deviations are the same, the curves end up looking very similar, right? Because the main difference in terms of the height of the curve is defined by the standard deviation. And so if you have the same standard deviation, then you should have the same height. And if you're looking at that and thinking, wait, but how come aren't there some other differences? No, that's exactly it. There are no other differences. The things when it comes to going through and representing distributions, the only things are the mean and the standard deviation. There's nothing else that separates them. And so because of that, you get this really interesting result. And then in terms of the fact that the graphs are not on top of each other, that's because the means are different. And so they're shifted versions of each other. So this curve here is exactly the same in every way as this curve, again, because the standard deviations are the same. But this one, the mean is at 64. This one, the mean is at 69. All right. So we discussed in the last section the idea of going through and finding probability using continuous probability distributions. All right. Since the normal distribution is a continuous probability distribution, we can go through and use the ideas from the last section to find probabilities. In particular, we can find the area under the curve. I should probably capitalize these. Normal distribution is a title. Since the normal distribution is a continuous probability distribution, we can find probabilities by finding the area under the curve. Over a given region. So, for example, what if we wanted to go through and find the probability that a randomly selected woman is taller than 62 inches? Or we wanted to go through and find the probability and all this is the same. A randomly selected woman is between 62 and 67 inches. Or we could find probability, all this is the same, is less than 62 inches. So how would we do that? Let's look at a picture, or a group of pictures, actually. All right, so we've got 3 pictures here to represent each of those 3 circumstances. So if we wanted to go through and find the probability that a randomly selected woman is taller than 62 inches, first we go through and we sketch a normal distribution, that is the bell shape here. And then we would go through, and so we know the mean is at 64. So to the left of the mean, we want to just pick a spot that we would represent as 62. And then since it's taller than 62, we just want to go through and everything to the right of 62 is what we want to go through and find the area of to get the probability. If we wanted to go through and find the probability that a randomly selected woman is between 62 and 67, then again, you want to draw yourself a picture. You want to go through and put 64 on there, put 62 to the left of 64, put 67, and then we just want to find the area that is under the curve between those two. That area is going to be the probability. And then finally, if we want to find the probability that a randomly selected woman is less than 62, then you've got your distribution here. You could put 64 on there, put 62 to the left of it, and then shade to the left of it. What we want to do is we want to find the area under the curve that is to the left of 62, and that's going to give us the probability that a randomly selected woman is less than 62, is less than 62 inches of height. Okay, so each of these pictures here, I've gone ahead and I've given them to you. So what the text recommends is that you go and you sketch them yourself. So I wanted to go through and sketch, 1 or 2 of these just so that we can kind of show, what that looks like. I kind of just described it, but it's one thing to have it described and it's another thing to be shown it. Okay, so let's say you want to go through and find probability that a woman is greater than 62 inches. So how do you go through and sketch that? So what you want to do is you want to start off ahead and draw yourself some coordinate axes here. So this has density, and then this has height. Start off, pick a spot. So we know the height is 64, so that we know the mean is 64. So go ahead and throw that on there. And then you just want to draw that bell shape where the peak is at 64. And I probably will do a terrible job here because I'm using a writing tablet, but just do your best. Okay, that wasn't nightmarishly bad, but good enough. And then what you want to do is we want to go through the probability the woman is greater than 62. So just pick a spot over here, put 62, draw a vertical line. And then what we want to do is we want to go through and find the area over here. And so we're just going to I'm going to do the best I can to shade this. Can't really do shading with a writing tablet, but the idea is we want to go through and find this area. The shaded area is the desired probability. So that's how you can go and sketch it. If you want to do a little bit better job than this, one of the things you can do is that we do know the standard deviation. So you could go and you could throw the standard deviations on here too. So we know the standard deviation is 1. So you could go through and you could put 61 and 58 on here, and put some standard deviations. That would be adding a little bit more detail, but you don't need to do that. All right. So that's the idea. That's the connection between the last section and this section, is that the area under a continuous probability distribution gives us the probability for a given outcome. So the next thing we want to do is to actually go and calculate it. So what we just did was not calculating it. It was just kind of connecting the two sections. And so to go through and actually do that, to actually do the calculations, we're going to use StatCrunch. Where is StatCrunch? All right, hold on. I'm going to pause the video while I try and find it. Okay, I have located it. All right, so once you've got StatCrunch opened up, what we want to do is we want to go to Stat. There it is. I was like, where is it? Under calculators, stat, and then go to normal. All right, and look at that. A normal distribution appears. Okay, do I need to reshare that, or is that? No, that looks right. Okay. And so if you want to go through and use this, there's a bunch of different options here. So let's just kind of walk through them. All right. So first of all, the default is this is the selected standard. So standard is finding a probability that's to one side. All right, so one-sided probability. If you want to do between, then you click on between. Shocking, right? And then you suddenly, and that opens up the option to go through and find the area or / probability that's between two values. All right, so you've got to the left and between. Okay, so I assume if you want to, you could probably change this. Yep, you can make it greater than. So you can go through and if you have one-sided, you can change the side by selecting less than and greater than. All right, now the values that are down here, these are of course critical. They start off in terms of z-scores. So we covered z-scores earlier in the semester. You can go through and take the mean and the standard deviation and convert them to z-scores, and then go through and enter the z-score values and do the probabilities that way. Maybe I'll do that just so you can see the calculation, but you don't need to. Instead, what you can do is you can actually enter the mean and enter the standard deviation. So what we want is we're looking at the heights of women, and we know those have a mean of 64. So just change that to 64, and we know that they have a standard deviation of 3. When you're done, hit enter. And then what you're going to find is you have your curve there. And now now the curve is centered at 64. And it tailors off, the bell shape here aligns with the standard deviation of 3. Okay, so if we want to go through and do probabilities, now it's just a matter of entering stuff in here at the bottom. So what we want to go through and do is we want to find the probability. Let's see, what was the first one we want to do? So greater than 62. All right, so let's change this. We're going to change this to greater than. All right, and then we can just enter in here 62. And if you go ahead and hit enter, then suddenly it goes through and it shades greater than 62 so that we can see visually what it's giving us the value for. And then the probability, or the area under the curve, those are the same thing, right? Those are the same things. You got to get that into your head. It's around 75%. So there's about a 7. So what does that mean in terms of interpretation? It means that there's about a 75% chance that a random selected woman is going to be taller than 62 inches. All right, and so that's how to go through and get that result. Now let's go through and say we wanted to do, what was the next one? It was between 62 and 67, I believe. All right, so yes, between 62 and 67. So how could we calculate that probability? So you can click between, all right, and take a look. So it defaults to z-scores, which don't make much sense in this case. So you want to change those over to, right, it being between. So between the low end is 62 and the high end is 67. And then when you're done, you can hit enter or compute and take a look. It goes through and it shades the part of the bell-shaped curve, the part of the normal distribution that we're interested in finding the probability of, and it tells us the probability, is about 59%. So there's about a 59% chance if you go through and select a random woman that that the height of that woman would be between 62 and 67 inches. All right, and then the last one was less than 62 inches. So if we want to do less than, we need to shift back over, and then we want less than, and the 62 just stays there, and boom, it just gives it to us about 25%. Okay, and just as a refresher, I haven't mentioned it, and that is that the entire area under the curve does fit within the definition of the last section, where we said the entire area has to be 1. So we get in this case, the shaded piece, this is 0.25 of a total area that's 1. And pardon me, if you know that, then you can actually look at the first result, which was about 75%, about 0.75, and those two are complements of each other, to tie this in with the last chapter. And so if you go through and you take the probability that someone is less than 62 and the probability that someone is greater than 62, those are opposites, those are complements, and so you're going to get values, 1 minus one result is going to give you the other result. Okay, and so before I forget, actually, let's go ahead and do the calculation with z-scores. All right, so how do we translate all this into z-scores? So as a quick refresher, the formula for z-scores, you've got result minus the mean divided by the standard deviation. Okay, and notice I'm using the mean and standard deviation for the probability distribution. I think that's the right thing to do. Anyway, that's a detail. All right, so what we want to do is we want to go through and translate everything over. So we've got we know that the mean, right, is going to be 64. We know that the standard deviation is 3. And then so we could go through and find the z-score for 62. That's going to be 62 minus 64 divided by 3. So that's -2/3. Okay. Let's just go ahead and just bang out all these, bang out the other one too. All right. So what about 67? So 67 minus 64 over 3. That's going to be 3/3, which is 1. Okay. And so let's see if we can go through and get the same values using these. So we've got -2/3 and 1. All right. So if you're going to go through and use z-scores, then the mean for z-scores is 0, and the standard deviation for z-scores is always 1. Okay. And then so if we want to find the probability, so now let's go through and do them in the same order that we did before. So we had greater than, and so we want it greater than, so we're not using 62 now, we're going to use the equivalent of that. So that was what, -2/3. Let's see if it will just let us enter it like that, or do we need a decimal? Nope, that works just fine. So we enter -2/3, and we get the exact same result that we did earlier with, with the non-z-score values. Sorry, with the non-z-score values. And so you could then swap this around, and boom, you get 0.25, and then we could do between, and so we're going to have -2/3, and then 67 had z-score of 1, and then compute, and again you get the same value we did earlier, which is about 59%. All right, and so you can go through and use z-scores to calculate the probabilities as well. All right, let's look at another example. So we just, all this time we've been working on this same the same examples. Let's look at a second example. And the example we're going to look at is the mean length of newborn seals. All right, and so we're going to say the mean is 29.5 inches. And the standard deviation is 1.2 inches. And we want to find the probability that a random seal is within 1 standard deviation of the mean. And just for practice, we could go ahead and draw a sketch of this. We've got put your axes. We've got 29.5. Go ahead and draw the bell shape. It should probably level off a little faster than that, but anyway, you get the idea. And then within 1 standard deviation, so if we go 1 standard deviation in each direction, so 1 standard, we want to subtract 1.2, so we're going to have 28.3. And then over here, add 1.2, we're going to have 30.7. So we want to know the area that's under the curve that's within 1 standard deviation each way. Now, if you're getting flashbacks to earlier in the course where we talked about the empirical rule, that's a good thing, because all of this does connect with the empirical rule. The normal distribution does match with the empirical rule. And what does the empirical rule say is the the amount of the stuff that's between one standard deviation. It says that the portion of the whole, it should be about 68%. So 68% is within one standard deviation. Let's see if we do get that as our outcome. Here's a hint, but we should. All right, so there's a couple ways we could go through and do this. And if we just leave it with z-scores, instead of popping in the mean and the standard deviation, we're almost there. The only thing we need to do is just change that to -1. And then what we've got is the mean is 0, standard deviation is 1. That's true for all z-score defined systems. And then all z-scores define normal distributions. And then we just put from -1, from one standard deviation to the left to one standard deviation to the right, hit enter, boom, 68.2%. All right, and so that's our empirical rule right there, coming back from early in the semester. Isn't it kind of neat how everything fits together eventually? And so that's where that came from. And if you want to, you could enter the actual mean and the actual standard deviation and the actual values, and you'll get the same result. But I'm not going to, because it's cooler to use z-scores. Z-scores are considered more sophisticated. All right, what's the probability that a randomly selected seal is longer than 30.7 inches? And you know what, just to, well, actually, let's go through and do it with the actual data. Just to, I was going to turn this into z-scores and just keep using z-scores, but my guess is that most of you guys are probably not going to use z-scores. So let's go through and punch in the actual data so that the second example can give you a kind of a second representation for how to do it. All right, so what do we want here? We want is longer. All right, so longer, that's not between, that's one-sided. And that's longer is going to be a greater than measure. And then we want to throw the mean in here. What was the mean? 29.5. And the standard deviation, that is 1.2. Right. And then what do we want to know? We want to know greater than 30.7. And then hit it. All right, and what we get is we get about 16%, 0.158. All right, and so that gives us the probability. Oh, some things I forgot. I was going to mention, well, not things. One thing I forgot. You can actually, so now that we've talked about the empirical rule, you can actually see the empirical rule results. Remember the empirical rule? So it said 68, 95, and then close to 100. That close to 100 is a 99.7. If you go ahead and click on this, what happens is the graph is oriented so that it fits to that. You know what? Hold on. Let's see it. What happens if I take this out? You have to specify. Hold on. Let's try this again. All right, so we've got 29.5 and 1.2. All right, you got your picture there. Now click on it. Oh, it didn't work. I got it earlier so that it would go through. Oh no, it did work. All right, so you can see here we've got one standard deviation. That's one standard deviation. So one standard deviation to the left is 28.3. Two standard deviations, 27.1. So if you click that button, it should reorient the graph, and so that the standard deviations are marked. So that's just what I wanted to show you, is that this button here, if you click it, it will go ahead and it will give you the tick marks for, I mean, it even says it, the ticks, right? The tick marks for the standard deviation. So that's kind of cool. Well, let's jump back to our whiteboard here because we're not quite done. The last thing we're going to talk about is reversing the process. So suppose we wanted to go through and find measurements given percentiles / probabilities. Right, so let me just be kind of clear about what I mean by that. So what we have been doing is we've been going through and we've been entering a measurement. So for example, what we just did, the 30.7, that was a measurement. So we were entering a measurement. We want to know the probability that seals were greater than that. So we were entering 30.7, and then out was coming the probability. The probability was produced when we hit enter. With StatCrunch. So this next section is, what if we wanted to go the other way? What if we wanted to enter a probability and then out would come a measurement, just the opposite, okay? So let's, I wrote some notes for this. Let me write those down. So I'm just gonna write out what I just said. Suppose we want to reverse the process. We want to enter a probability and find the measurement that generates that probability. That's the opposite of what we've been doing. All right, so an example. I think the easiest way to describe this is with an example. All right. We want to find the length of a baby seal where the probability that a randomly selected seal with less than that length is 11%. So it's wordy, but it means it's the opposite of what we've been doing. All right, so what we've been doing is we've been going through and we've been entering the length, and then out was coming the 11%. What we want to do is we want to enter the 11%, and then out comes the length of the seal. All right. So, what we know from the stuff that we've looked at previously, we know this is the length where the area under the curve that's less than that is going to be 0.11. So let's draw ourselves a picture. So what we're looking for, we've got our normal distribution. That's a really terrible looking one. That's okay. And the idea is that we've gone through and we've actually, let me use the line tool so that it doesn't look, oh, whoops. Right. And so what we've got is we know that this is a 11% or 0.11. And what we want is we want X. All right. We want to know what is the length that goes with an 11% probability. And an 11% probability is the same thing as, the area under the curve is 0.11, because area under curve and probability are connected for continuous probability distributions. Okay, and so we know that this is the length where the area under the curve is going to be that's less than that length. The area under the curve that's less than that length is 0.11. All right, so we're going to go through, and I used this term earlier in the semester, but this is also called the 11th percentile. Right, so if you've got a mark on your distribution, and that goes through and separates the bottom 11% of the data from the top 89% of the data, that's called the 11th percentile. Okay, and so just to give you another example, another point of context, if we had the mean, right, if we went through and put the mean on here, what was it? I can't remember. It was 29.5, I think. So we have 29.5. All right. So what percentile is the mean? All right. So think about what data is to the left of that. How much data is to the left of that it's separating from the data to the right of that? Well, it's separating. It's in the middle. So if it's in the middle, it's separating the bottom half from the top half. So the mean is the 50th percentile. So 29.5 is the 50th percentile. That's how percentiles work. Okay, so we want to go through and find the 11th percentile. That's the same thing as finding the location where 11% of the area is to the left of that. So how do we go through and do that? StatCrunch. Let's jump back to StatCrunch. So we've got 29.5, we've got 1.2. All right, so how does this work? So if you want to go through and figure out the location where you have 11% probability, what you're going to do is you're going to open this up so that it's empty. And then you're going to go to the probability. So before we entered a number here and then hit compute and a number here appeared. Now we're going to enter the probability and then a number here is going to appear. All right, watch. All right, so we want to enter 0.11 for 11%, or the 11th percentile. And then, assuming I did this correctly, I tried this beforehand, hit enter, and then boom, the 11th percentile appears there. It is 28.028 inches. All right, so our answer is going to be 28 point, we'll round it to 2 decimal places, 28.03 inches. All right, so it is 28.03 inches is the answer. All right, I believe we've got another one. Okay, yeah, so find the 25th percentile for women's heights. Okay, so it's important to be able to connect this to probability. So what we're trying to find is we're trying to find the height where where the probability of less than that height is going to be 25%. So we're trying to find the height where the probability of a randomly selected woman is going to have 25% probability for less than that height. All right, so to do that, you jump back over to our StatCrunch. We're going to enter the information. So the mean is 64. The standard deviation is 3 for the height of a woman. We're going to leave this empty. All right. And then we can go in and what do we want? We want the 25th percentile. And so that's 25% or 0.25. Enter and boom, 61.98 inches. So again, what did we just produce? We produced the number where the probability of a woman having a height less than that number is going to be 25%. All right. And so anyway, you can play around with this to calculate other probabilities. You can do greater than. If you do greater than, open this up. You could type in, 0.6. What's the height where the probability is going to of randomly selecting a woman is going to be 60% for greater than that height. Okay, hit it, boom, 63.24 inches. So there is a 60% probability that a randomly selected woman is going to have greater than 63.2 inches. You can also do between with this, although it gets a little weird. So you have to specify one of the two ends. All right. And so if we go through and say, we want to know, so we've got 62 is the bottom end, leave that empty. And then if you enter, all right, so we want to go through and find the top end where the probability would be, let's say 50%. So we want to go through and find the top end of the range from 62 to what's the top end where we'd end up having a probability of 50%. Hit it, 66.047. So the probability of randomly selecting a woman whose height is between 62 and 66.0471 inches is 50%. Okay, and you can also leave the bottom end blank and do I don't know, 67, and then we could do 0.3. And so you could say, all right, well, I want to go through and find the height so that a randomly selected woman between that height and 67 inches, there's a 30% chance that we end up getting a woman who has a height in that range. Boom, hit it, and it's 64.3. All right, and so you can do all manner of different combinations when it comes to the StatCrunch tool. You can enter the height, get out the probability, enter the probability / percentile, get out the height. It goes both ways. And I think that covers everything. I think that covers out all the different possibilities. And of course, all of that can be done with z-scores as well. So I think that's it. I think that's it for this video. Thank you for watching. I'll see you next time.